Hello dear students, all of you welcome to Vidyan classes. It is the sixth lecture on relations and functions. Today we will discuss some J level questions. First question, so that the relation phi is not reflexive but symmetric and transitive on the non-empty set capital A. Proof. Given phi is the relation on A. To show phi is not reflexive but symmetric and transitive on capital A. Phi is the relation on A. To show phi is not reflexive but symmetric and transitive relation on A. Clear? Test for reflexive. What is reflexive relation? The relation capital R on A is said to be reflexive if for all x belongs to capital A, x's order pair belongs to R. Here R is phi. For all x belongs to given set is a xx order pair does not belongs to R. That means phi. The statement, this statement does not satisfy the definition of reflexive. The statement, this statement does not satisfy the definition of reflexive. Therefore, the relation phi is not reflexive. The first condition is satisfied, that is phi is not reflexive. Test for symmetric. What is the definition of symmetry? XY order pair belongs to R. That implies YX order pair belongs to R. XY order pair does not belongs to R. R means phi. Implies YX order pair does not belongs to R. XY order pair does not belongs to phi is true. YX order pair does not belongs to phi is true. That is the statement satisfies the definition of symmetric. Clear? Okay. Therefore, the relation phi is symmetric. R is symmetric. If xy belongs to R, that implies yx belongs to R. Here R is phi. Or we can say xy order pair does not belongs to phi, that implies yx order pair does not belongs to xy order pair does not belongs to R, that implies yx order pair does not belongs to R. Clear? Okay. Transitive. What is the transitive? The relation R on A is said to be transitive if xy order pair belongs to R, yx order pair, yz order pair belongs to R, that implies xz order pair belongs to R. Or we can say xy order pair does not belongs to R and yz order pair does not belongs to R, that implies xz does not belongs to R. xy order pair does not belongs to phi is true, and in negative sense yz order pair does not belongs to phi, that implies xz order pair does not belongs to phi. xy order pair does not belongs to phi is true, yz order pair does not belongs to phi is true, that implies xz does not belongs to phi is true. The statement, this statement satisfies the definition of transitive. xy order pair belongs to R, yz order pair belongs to R, xz order pair belongs to R, or we can say xy order pair does not belongs to R, yz order pair does not belongs to R, that implies xz order pair does not belongs to R, is also the definition of a transitive. Here the relation is phi. The statement is true. The statement satisfies the definition of a transitive. Therefore, phi is the transitive relation on A. In general, phi, the relation phi, in general the relation phi is not reflexive but symmetric and transitive on where A is the non-empty set. Hence the statement is proved. Hence proved. Clear? Clear? Okay. Note down. Second question. Is phi an equivalency relation on itself? Justify. Solution. Is phi an equivalency relation on itself? Yes. Reason. Phi is the relation and the given set is phi. Is an equivalence relation. Phi is an equivalence relation on itself. We have to test phi satisfies the definition of reflexive, symmetric and transitive. Test for reflexive. For all x does not belongs to phi, is it true? X's order pair does not belongs to phi. The given set is phi and the relation is also phi. Phi is an equivalence relation on itself. The given statement is true. R is reflexive for all x to the given set, x's order pair belongs to R, or we can say R is reflexive for all x doesn't belongs to A, x's order pair doesn't belongs to R. It is satisfied the second definition. The statement satisfies the definition of reflexive. Therefore, the relation phi is reflexive on phi, that is itself. So the relation phi is reflexive. Symmetric. XY order pair does not belongs to phi. Is it true? Implies YX order pair does not belongs to phi. Is also true. The relation R on A is said to be symmetry. XY order pair belongs to R. That implies YX order pair belongs to R. Or we can say the relation R on A is symmetric. If XY order pair belongs to R, that implies YX order pair belongs to R. The statement, the above statement satisfies the definition of symmetric. Therefore, the relation phi is symmetric on phi. R is reflexive, R is symmetric. The above statement means XY order pair belongs to phi is true. That implies YX order pair doesn't belongs to phi is true. The statement satisfies the definition of symmetric. Therefore, the relation phi is symmetric on phi. Test for transitive. XY order pair doesn't belongs to phi is true, and yz out of pair doesn't belongs to phi is true. That implies xz doesn't belongs to phi is also true. The statement satisfies the definition of transitive. Therefore, the relation phi on phi is transitive. In general, the relation phi is equivalence in general the relation phi is equivalence on phi. Equivalence means replacive, symmetric and transitive. The relation phi is replacive, the relation phi is symmetric, the relation phi is also transitive. In general, we can say the relation phi is equivalence on phi. Hence proved. Phi satisfies the definition of replacive, symmetric and transitive. Clear? Okay. Note down. Next question. Prove that intersection of two equivalence relations is an equivalence relation. Prove. Let R1 and R2 be two equivalence relations on the non-empty set capital A. Let R1 and R2 be two equivalence relations on the non-empty set capital A. We have to show intersection of two equivalence relations is an equivalence relation. That means to show R1 intersection R2 is an equivalence relation, which implies and implied by R1 intersection R2 satisfies the definition of reflexive, symmetric and transitive. Equivalence means the relation satisfies the definition of reflexive, symmetry and transitive. Test for reflexive. For all x belongs to the given set, that is A, XX order pair belongs to R1 and XX order pair belongs to R2. Since R1 and R2 are equivalents, that means R1 and R2 are reflexive. R1 and R2 are reflexive. R1 is reflexive. That means for all x belongs to capital A, XS order pair belongs to R1. R2 is reflexive. For all x belongs to capital A, XS order pair belongs to R2. Clear? Which implies for all x belongs to A, it is the definition of intersection. XX order pair belongs to R1 intersection R2. Now we have XS for all x belongs to capital A, XS order pair belongs to R1 intersection R2. It is the definition of reflexive. Therefore, R1 intersection R2 is reflexive relation on capital. Clear? The relation R1 R2, R1 intersection R2 is reflexive. Second, symmetric. XY order pair belongs to R1 intersection R2. By the definition of intersection, XY order pair belongs to R1 and XY order pair belongs to R2. Clear? It is the definition of intersection, which implies YX order pair belongs to R1 and YX order pair belongs to R2. Since R1 and R2 are equivalents, that means R1 and R2 are symmetric. Since R1 and R2 are symmetric relations on A. R1 is symmetric. That means XY belongs to R1. That implies YX belongs to R1. R2 is symmetry. That means XY order pair belongs to R2. That implies YX order pair belongs to R2. Clear? It is the definition of intersection. YX order pair belongs to R1 intersection R2. Now we have XY order pair belongs to R1 intersection R2. That implies YX order pair belongs to R1 intersection R2. XY order pair belongs to R1 intersection R2. That implies YX order pair belongs to R1 intersection R2. Therefore, it is the definition of a symmetric R1 intersection R2 is symmetric relation on the third transitive. Transitive. XY order pair belongs to R1 intersection R2 and YZ order pair belongs to R1 intersection R2. We have to show XZ belongs to R1 intersection R2 so that the relation R1 intersection R2 is transitive. By the definition of intersection, XY order pair belongs to R1 and XY order pair belongs to R2. This implies to this, and YZ order pair belongs to R1 and YZ order pair belongs to R2. Clear? Clear? Okay. Which implies this XY order pair belongs to R1 and YZ order pair belongs to R1 and XY order pair belongs to R2 and YZ order pair belongs to R2. Since A intersection B intersection C intersection D is the same as A intersection C intersection B intersection D. Intersection is present everywhere, so we can interchange any two. Clear? Since XY belongs to R1 and YZ belongs to R1, XZ belongs to R1 and XY belongs to R2 and YZ belongs to R2, that is XZ belongs to R2. Since R1 and R2 are equivalents, that means R1 and R2 are transitive. R1 and R2 are transitive relations. X to Y, Y to Z, that is X to Z. XZ belongs to R1 and XZ belongs to R2. By the definition of intersection, XZ belongs to R1 intersection R2. Now we have XY belongs to R1 intersection R2 and YZ belongs to R1 intersection R2. That implies XZ belongs to R1 intersection R2. XY belongs to R1 intersection R2. YZ belongs to R1 intersection R2 implies xz belongs to R1 intersection R2. Therefore, R1 intersection R2 is the transitive. R1 intersection R2 is the transitive. R1 intersection R2 is the symmetric. R1 intersection R2 is the reflexive. In general, R1 intersection R2 is an equivalence relation on hence proved. Hence proved. Here, okay. Note down. Next question. Find the least positive integer x satisfying 276x plus 128 congruous to 4 modulo 7. By the division of algorithm, we can find out the remainder. 276 is divided by 7. 7 into 9, that is 63. The remainder r is equal to 3. Two 76 congruence to 3, since the remainder is 3. 276 minus 3 is divisible by 7. X congruence to x mod 7. Since x minus x, that is 0, is divisible by 7, which implies 276 x congruence to 3x mod 7. Since A congruence to B mod M, C congruence to D mod M implies SC congruence to BD mod M. A congruence to B mod M, C congruence to D mod M, that implies SC congruence to BD mod M. By this principle, we have this. It is the equation 1. Again, 128 is divided by 7. 7 8 56, that is the 2. Here the remainder is the 2. That means 128 congruence to 2, since the remainder is the 2, mod 7. That means 128 minus 2 is divisible by 7, equation 2. From equation 1 and 2, we get 276 into x plus 128 is equal to 3x plus 2. 276x plus 128 congruence to 3x plus 3x plus 2. Since A congruent to B mod M, C congruent to D mod M implies A plus C congruent to B plus D mod M. A congruent to B mod M, C congruent to D mod M, that implies A plus C congruent to B plus D. So equation 1 and 2 implies this. It is a 3. It is given by 276 x plus 128 congruent to 4 mod 7x. It is equation 3. It is equation suppose 4. Clear? From equation mod 4, mod 7. Equation 3 and 4, we have the left side is 0 and the right side is 3x plus 2, 0 congruent to 3x plus 2 minus 4. This minus this. Mod. Since these are the properties of a congruence modulo, we have discussed these properties in previous class. A congruence to B mod M implies A plus x congruent to B plus x mod M. Since this condition is satisfied, where x belongs to Z, or A minus x congruent to B minus x mod, where x belongs to Z. So this minus this is congruent to this minus this. Now we have 0 congruent to 3x minus 2 mod 7 implies 3x minus 2 minus 0 is divisible by 7 divides this, which implies 3x minus 2 is equal to 7k. K belongs to Z set. X is equal to 7k plus 2 divided by 3, which implies x is equal to 3 for k is equal to 1. Is the least positive integer satisfying this condition. Therefore, the least positive integer is x equal to 3. The other values of x are, since the modulo is 7, 3 plus 10, that 3 plus 7, that is equal to 10. 10 plus 7, that is equal to 17. Next 24. And the modulo is 7. The next value of x is 3 plus 7, that is equal to 10. The next value is 10 plus 7, that is 17. 17 plus 7, that is equal to 24. And so on. But the least positive integer is x, that is equal to 3. Here it is the application of a division of a algorithm and congruence modulo relation, properties of a congruence modulo relation. Clear? Okay, no doubt. Next question. So that congruence modulo 2 relation partitions or decomposes the set Z into disjoint equivalence classes. In the previous class, we have discussed congruence modulo relation decomposes or partitions the given set into disjoint equivalent classes or identical equivalent classes. What is equivalent class? Let A belongs to Z. Equivalent class of A modulo 2 is the collection of x such that A congruous to x mod 2. Congruence modulo is an equivalence relation. Here this relation is read as congruence modulo relation, which is an equivalence relation. We have to show congruence modulo 2 relation partitions or decomposes the set Z into two disjoint equivalent classes. Equivalent class of A modulo 2 is the collection of x so that A congruous to x modulo 2. A belongs to Z. For A is equal to 0 implies S. Equivalent class of 0 modulo 2 is the collection of x so that A minus x is divisible by 2. 0 minus 0 divisible by 2. Here the modulo is 2. 0 plus 2, that is equal to 2 plus 2 is equal to 4. 4 plus 2 is equal to 6. And dot dot. 0 minus 2, that is minus 2. Minus 2 minus 2, that is minus 4. Minus 6 dot dot. A minus x divisible by 2. That is here A is 0, these are x. 0 minus 0 divisible by 2, 0 minus 2 divisible by 2, 0 minus 4, that is divisible by 2 and so on. So equivalent class of 0 modulo 2 is the set containing 0, 2, 4 dot dot minus 2, minus 4, minus 6 dot dot. For A is equal to 1. Equivalent class of 1 modulo 2. Here A is equal to 1. The values of x are 1 minus 1, that is equal to 0 divided by 2. Since the modulo is 2, 1 plus 2, that is equal to 3. 3 plus 2, that is equal to 5. 5 plus 2, that is equal to 7. And so on. 1 minus 2, that is minus 1. Minus 1 minus 2, that is minus 3 dot dot. Is the equivalent class. 1 minus of minus 3, that is equal to 4 divisible by 2. 1 minus of minus 1, that is equal to 2 divisible by 2 and so on. For A is equal to 2 implies yes. Equivalent class of 2 modulo 2 is the collection. 2 minus 2 divided by 2. For 1 it is 1. For 0 it is 0. For 2 it is 2. 2 plus 2 modulo is 2. 2 plus 2 that is equal to 4. 4 plus 2 that is equal to 6 and so on. 2 minus 2 that is equal to 0. 0 minus 2 minus 2 minus 4 and so on. Which is same as equivalent class of 0 modulo 2. This set is same as this set. Similarly, equivalent class of 0 modulo 2 is same as equivalent class of 0 modulo 2 equivalent class of 4 modulo 2. 0 modulo is 2. 0 plus 2 that is 2. 2 plus 2 is equal to 4. 4 plus 2 that is equal to 6. Similarly, we can show it. 0 minus 2 that is minus 2 modulo 2 and minus 4 equivalent class of minus 4 modulo 2 and so on. And equivalent class of 1 modulo 2. 1 plus 2 that is equal to 3. 3 plus 2 that is equal to 5 since the modulo is 2 and dot dot. 1 minus 2 that is minus 1. Minus 1 minus 2 that is minus 3 and minus 3 minus 5. Here modulo 2 modulo 2 modulo 2. Clear? So there exist only two equivalent classes. These two equivalent classes are disjoint to each other. So there exists only two equivalence classes. They are equivalent class of 0 modulo 2 and equivalent class of 1 modulo 2. Satisfying they are equivalent class of 0 modulo 2 and equivalent class of 1 modulo 2. Satisfying union of equivalent class of 1 modulo 2 union equivalent class of 2 0 modulo 2 is equal to Z set. And intersection of equivalent class 0 modulo 2 intersection equivalent class of 1 modulo 2 is equal to R. Equivalent class 0 and equivalent class of 1. Other equivalent classes is same to equivalent class of 0 or equivalent class of 1. Two equivalent classes are identical to each other. These are identical or disjoint to each other, but this and this are disjoint to each other. Two equivalent classes are identical to each other or disjoint to each other. Union of all equivalent classes. Here for modulo 2 there exist two equivalent classes, that is the equivalent class of 0 and the equivalent class of 1. Satisfy these two conditions. Hence the statement is proved. So that the congruence modulo 2 relation partitions or decomposes the set Z into two equivalent classes. Hence proved. Hence proved. Similarly, for modulo 3, there exist 3 equivalence classes. They are equivalent class of 0 modulo 3, equivalent class of 1 modulo 3 and equivalent class of 2 modulo 3. And they are equivalent class of 0 modulo 3, equivalent class of satisfying equivalent class of 0 modulo 3 union equivalent class of 1 modulo 3 equivalent class of union modulo 3 is equal to Z set. Intersection of any two is phi. Equivalent class of 0, 3 is equal to phi. Equivalent class of 1 intersection 2 also phi. And equivalent class of 0 intersection equivalent class of 2 is equal to phi. Clear? In general, for modulo M, the equivalence classes are equivalent class of 0 modulo M, equivalent class of 1 modulo M, equivalent class of 2 modulo M, dot equivalent class of M minus 2 modulo M and M minus 1 modulo M. For modulo 2, there exist two equivalent classes, that is equivalent class of 0 and equivalent class of 1. For modulo 3, there exist three equivalent classes, they are equivalent class of for modulo 3, there exist three equivalent classes, they are equivalent class of 0, equivalent class of 1, equivalent class of 2, satisfying these conditions. Union is the adjacent and intersection of any two is phi set. In general, for modulo M, the equivalent classes are this. That means for modulo 2, 2 equivalent classes. For modulo 3, 3 equivalent classes. For modulo M, there are M equivalent classes. Clear? And satisfy equivalent class of 0 modulo M union equivalent class of 1 modulo M union equivalent class of M minus 1 modulo M is equal to Z set. And the intersection of any two equivalent class of 0 modulo M intersection equivalent class of 1 modulo M is equal to phi. Dot equivalent class of and so on. Any two equivalent class of M minus 2 M intersection equivalent class of M minus 1 of M is equal to phi. In general, we can say intersection of these all are disjoint to each other, so intersection must be high. Any two, or in general, intersection of this intersection this is also phi. Clear? Clear? Okay. Next question. Find least 3 positive integers xi, I varies 1 to 3, satisfying 3x congruent to 2 modulo 7. Solution: 3x congruent to 2 modulo 7, which implies 7 divides 3x minus 2. A congruent to B modulo m implies m divides a minus b. Here a is 3x, b is 2. 7 divides 3x minus 2, which implies 3x minus 2 by 7 is equal to k, where k belongs to z set, which implies 3x minus 2 is equal to 7k, which implies x is equal to 7k plus 2 by 3. Clear? Okay. For k is equal to 1 implies x is equal to 9 by 3, that is equal to 3, which is equal to x1. We have to find out least 3 positive integers. 3x congruent to 2 modulo 7. x1 is equal to 3 plus 7 is equal to 10. x2. x3 is equal to 10 plus 7, that is equal to 17. Since equivalent class of A congruence modulo is an equivalence relation. Equivalence relation decomposes or partitions the given set into disjoint equivalent classes. A belongs to Z. Equivalent class of A modulo M is the same as equivalent class of A plus M modulo M, which is same as A plus 2M modulo M. Here, in the previous class, we have discussed two equivalent classes are identical to each other or disjoint to each other. Equivalent class of A modulo M is same as equivalent class of A plus M modulo M, which is same as equivalent class of A plus 2M modulo M. Here A is equal to x1, that is equal to 3. x2 is equal to A plus M, that means M is equal to 7. That is 3 plus 7 is equal to 10. x3 is equal to A plus 2M. That is equal to 3 plus 2 into 7, that is equal to 17. 3, 10, 17 satisfies 3x congruent to 2 mod 7. Therefore, 3, 10, 17, the least 3 positive integers 3 positive integers so that 3x congruent to 2 mod 7. That means 3, 10 and 17 satisfies 3x congruent to 2 modulo 7. If x equal to 3, 9 congruent to 2. That means 9 minus 2, that is 7, divisible by 7. If x equal to 10, it is 30. 30 congruent to 2. That means 30 minus 2, that is equal to 28, divisible by 7. Similarly, x equal to 17. 3 into 17, that is equal to 51. 51 minus 2, that is equal to 49. 49 divisible by 7. Therefore, 3, 10, 17 are 3 positive integers such that 3x congruent to 2 modulo 7. Clear? Okay. No doubt. Next question. Find least non-negative integer r such that 6 into 18 into 27 into minus 225 congruent to r modulo 8. What is the meaning of this expression? This expression implies r is the remainder obtained dividing 6 into 18 into 27 into minus 225 by 8. R is the remainder. It can be solved by the properties of congruence modulo relation and by the division of algorithm. Solution: 6 into 18 which is equal to 108. Dividing 108 by 8. Here the remainder is 4. Here the remainder is 4. And the quotient is 3. Implies 108 congruent to 4 modulo 8. Equation 1. 27 dividing 27 by 8. That is 3, which implies 27 congruent to 3 mod 27 minus 3, that is 24 divisible by 8. $225 by 8. 65. The remainder is 1. Dividing 225 by 8, the quotient is 28 and the remainder is 1. But it is given by minus 225. Minus 225 divided by 8. Here the quotient is 28. In this case, the quotient will be minus 29 to obtain the remainder as a positive. By the division of algorithm, the remainder is always greater than 0 or equal to 0. Eight into 9, that is equal to 72, 23 minus, that is equal to 7. The remainder is 7. Implies minus 225 congruent to 7 mod 8. It is the equation 3. From equation 1 and 2 and 3, from equation 1, 2 and 3, we have 108 congruent to 4 mod 8. Equation 2 implies this. It is equation 2. 27 congruent to 3 mod 8. And equation 3 gives minus 225 congruent to 7 mod 8. Which implies 108 into 27 into minus 225 is congruent to 4 into 3 into 7, that is equal to 4 into 3 into 7, which is equal to mod 8, which implies since by the properties of congruence modulo A congruent to B mod M, C congruent to D mod M, implies a C congruent to BD mod M. Clear? By this principle, we have this 108, that is equal to 6 into 8, 18 into 27 into minus 225 congruent to 4 into 3 into 7, that is 84. 84 is divided by 8. That is, the remainder is 4. Modulo it is 4. Equation 4. But it is given by 6 into 18 into 27 into minus 225 congruent to R. Given 6 into 18 into 27 into minus 225 congruent to R mod it is 5. Comparing equations 4 and equation 5, we get R is equal to. Find the least non-negative integer R so that 6 into 18 into 27 into minus 225 congruent to R mod 8. Therefore, R is equal to 4. Clear? Clear? Okay. Note down. Next question. So that the relation wiggly on Z given by wiggly is equal to set of a B order pair such that A congruent to B modulo 3 is an equivalence relation. Note the symbol. This symbol is pronounced as wiggly or tilde, which represent a relation. This symbol is pronounced or read as wiggly or tilde. It represents a relation. We have to show the relation wiggly is an equivalence relation. Solution. The relation wiggly, this symbol is read as wiggly or tilde, which represent the symbol of a relation on Z set, that is set of integers. The relation wiggly on Z is defined by wiggly is equal to set of a B order pair such that A congruent to B mod 3. A B order pair belongs to wiggly if this condition is satisfied. That means the difference of A and B is divisible by 3. To show the relation wiggly, is an equivalence relation, which implies by wiggly satisfies the definition of reflexive, symmetric and transitive. Test for reflexive. We have to show wiggly is an equivalence relation. That means wiggly satisfies the definition of reflexive, symmetric and transitive. First, test for reflexive. For all A belongs to Z, 3 divides 0 is true, which implies 3 divides A minus A, which implies A related to A. Here 3 divides is 0, that means 3 divides, or we can write, which implies A congruent to A mod 3. That implies a related. Here the relation is weakly. This symbol represents a relation. A related to A. Now we have for all A belongs to Z set, that means set of integers, A related to A. That means A order pair belongs to weakly. It is the definition of a reflexive. Therefore, weakly is a reflexive relation. Clear? Okay. Test for symmetric. A related to, here the relation is weakly. A related to B implies A congruence to B mod 3, which implies 3 divides A minus B. That implies A minus B by 3 is equal to K. K belongs to Z set, which implies B minus A by 3 is equal to minus of K. Minus K belongs to Z set, which implies 3 divides B minus A. That implies 3 divides B minus A. B congruent to A mod 3. That implies B related to A congruent to B mod 3. That means A related to B. Here the relation is weakly. Here the relation is weakly. B congruent to A mod 3 implies B related to A. A related to B implies B. Now we have A related to B, that implies B related to A. Therefore, the relation weakly is symmetric. Therefore, the relation weakly is symmetric. Clear? Okay. Note down. Test for transitive. Test for transitive. A related to B and B related to C. Let ABC belongs to Z set. So that A congruence to B mod 3 and B congruence to C mod 3. That implies 3 divides A minus B and 3 divides b minus c. Clear? By the definition of a congruence modulo relation, which implies a minus b by 3 is equal to k1 and b minus c divided by 3 is equal to k2, where k1, k2 belongs to z set, which implies a minus b is equal to 3k1 and b minus c is equal to 3k2, which implies a minus b plus b minus c is equal to 3k1 plus 3k2 is equal to 3k3, where k1 plus k2 is equal to k3 belongs to z set. Clear? bb cancel, a minus c is equal to 3k3, which implies a minus c divided by 3 is equal to k3, which implies 3 divides a minus c, which implies a congruence to c mod 3. 3 divides a minus c, that means a congruence to c mod 3, which implies a related to c. Now we have a related to b and b related to c, that implies a related to c. So therefore weakly is transitive. Now we have clear. Now we have weakly is reflexive, weakly is symmetric, weakly is transitive. Therefore the relation weakly is equivalence. Hence proved. Clear? Okay. Note down. Next, the relations R1 and R2 are defined by R1 is the set of xy order pairs such that y is equal to e to the x belongs to real set, and R2 is the collection of xy order pairs such that y is equal to e to the minus x belongs to real set. Then which of the following is true? R1 intersection R2 is equal to phi, R1 intersection R2 not equal to phi, R1 union R2 is equal to R square, that means square of a real set, and none of these. R1 is implies y is equal to e to the x belongs to real set. R2 implies y is equal to e to the minus x belongs to real set. Solving e to the x is equal to e to the minus x. That implies x is equal to 0. For x is equal to 0, implies yes, y is equal to 1. Clear? E to the y is equal to e to the x, y is equal to e to the minus x. E to the x is equal to e to the minus x equal to 0. For x is equal to 0, y is equal to 1. Implies as y is equal to e to the x and y is equal to e to the minus x meet each other at 0, 1. Y is equal to e to the x. If x increases, y increases and it meets at 0, 1. It is the graph of y is equal to e to the x. Here, if x increases, y decreases. So, its graph is y is equal to e to the minus x. It is the point of intersection of two curves. This point is the common point for both curves. The relation R1 and R2, in relation R1 and R2, there exists a common point, that is 0, 1. Implies R1 intersection R2 is equal to, here R1 is dash, there is R1 intersection R2 is equal to 5, R1 intersection R2 not equal to 5, is the intersection of contains 0, 1 order pair, so it is not equal to 5. There exists a common point in R1 and R2, that point is 0, 1 order pair. R1 and R2 are two relations. So the correct option is second. Second is the correct option. Clear? Clear? Yes, sir. Note down. Next question. The relations R1 and R2 are defined by R1 is the collection of xy order pair, so that y is equal to e to the x belongs to real set. R2 is the collection of xy order pair, so that y is equal to x belongs to real set. Then first bit R1 intersection R2 is equal to 5, second bit R1 subset or equal to R2, third bit R2 subset or equal to R1, fourth bit none of these. Here R1 implies y is equal to e to the x, R2 implies y is equal to x. Y is equal to e to the x, y is equal to x. Implies e to the x is equal to x as no solution. Implies y is equal to e to the x and y is equal to x never meet each other. y is equal to e to the x is an increasing function. That means y increases as x increases. It is the graph of the function y is equal to e to the x. X belongs to R. Y equal to x is the equation of a line. Y is equal to x is the equation of a line passing through origin. And its slope is 1. It is y is equal to x. There is no common point for both curves. That means the two curves never intersect each other. So R1 intersection R2 implies R1 intersection R2 is equal to R. So the correct option is the first. Since R1 and R2 has no common point. R1 and R2 has no common point. Since y is equal to e to the x and y is equal to x never meet each other. So the correct option is R1 intersection R2 is equal to 5. And it is the for x equal to 0, y is equal to 1. Clear? Clear? Next question. The relations R1 and R2 are defined by R1 is the collection of xy order pairs so that y is equal to 1 by x belongs to R, x not equal to 0. R2 is the collection of y is equal to xy order pair so that y is equal to minus x belongs to real set. Which of the following statement is true? Given R1 implies y is equal to 1 by x not equal to 0, x belongs to real set. R2 implies y is equal to minus x belongs to real set. Which implies y is equal to 1 by x, y is equal to minus x. 1 by x is equal to minus x. Since y is equal to 1 by x, y is equal to minus x. That implies s square is equal to minus 1. Is impossible. S square is equal to minus 1 is impossible. Square is never negative. Clear? Implies y is equal to 1 by x and y is equal to minus x. Never meet each other. Y is equal to 1 by x. That means xy is equal to 1. Implies x greater than 0, y greater than, or x less than 0, y less than 0. The product is 1. Both x and y are positive or both x and y are negative. Clear? So the graph of the function y is equal to 1 by x lies in first quadrant or in third quadrant. X and y are inversely proportional. Increase of x, y decreases, and decrease of x, y increases. It is the graph of the function y is equal to 1 by x for x greater than 0, y greater than 0. It is also the graph of the function y is equal to 1 by x less than 0, y less than 0. Clear? Okay. Again y is equal to minus x. Y is equal to minus x. If the equation of a line passing through origin, its slope is negative. That is theta is equal to 135 degree. It is the graph y is equal to minus x. This angle is 135. The two curves never meet each other. So there exists no common points between R1 and R2. Implies no common point between R1 and R2. Implies R1 intersection R2 is equal to phi. So the correct option is the first. R1 intersection R2 is equal to phi. Clear? Clear?